How's it going, ladies and gentlemen? Mr. Johnny here again, looking at 17.2 buffered solution stuff. All right, so it wants to know a combination of which of the following will make a buffered solution. Generally speaking, buffered solutions are made when you use a weak acid or base and you mix it with a salt that has its conjugate base pair or acid base pair. Salt, so with the conjugate. So if we take a look at our options, well, HI is a strong acid and its conjugate. Nope, we want a weak something. Weak acid or base. HBr, strong acid, not going to do it for us. HCl, strong acid, not going to do this. But if we look here, HF is a weak acid, and we got its conjugate base pair with the fluoride ion there. So D will help us. Basically, what's happening is we have a weak acid and we have its conjugate ion. So if I were to add H plus to that buffered solution, well, it's going to get taken up by the F minus to make more HF, right? Whereas if I were to add OH minus, well, it's going to react with the HF that's there to give us more fluoride ion and water. So it's resisting change in pH. If we take a look at number 2, it says adding hydrochloric acid and blank to water will make a buffered solution. So we know that HCl is a strong acid. All right, well, that's not going to help us a whole lot unless that chloride ion is like, of what's important. But if we take a look, all right, so we got a strong acid. Will adding this other acid to it? No, that's not going to help. Another acid to it? No. Ooh, maybe NaNO3, but nope. NO3 is the conjugate of another strong acid, so it's not going to be able to take up H+, right? So we basically have something that's going to resist change to OH minus if we were to add to it. But what is going to resist change if we add H plus to it? Not this. NaOH might work, but then when you think about it, what happens when you add HCl and NaOH? Because they're both strong acids and strong bases, they're just going to neutralize to give us H2O and salt, right? So that's not going to work. But we do know that NH3 is a weak base, right? So we know that if we add NH3 and we added H plus to it, well, it's going to take it up to make NH4 plus. It's going to make that ammonia ion, right? And then we have the HCl, which is going to resist the change from the OH minus to give us water and, whatever salt. So best answer here would be choice E. Number 3, what change will occur when a small amount of HCl is added to a solution containing fluoride ions and hydrogen fluoride? So we got fluoride ions and hydrogen fluoride, and we're adding HCl to it. Well, HCl is going to give us H plus and Cl minuses. So what? What's going to happen there? Well, the H plus is going to react with the fluoride ion because HF is a weak acid. So it likes to hold on to hydrogens, which is why it's weak. It doesn't give off hydrogens that well. It likes to hold on to them. So you start pumping in more H pluses. This fluoride ion is going to be like, yo, hey, let's hang out. Let's chill. What are you doing over there? Let's hang out. So you're going to make more HF. So HF is going to increase and the amount of fluoride ion is going to decrease. And if we take a look, I believe choice D says that. Concentration F minus ion will decrease, then HF will increase. All right, bada bing, bada boom. You might think, well, hey, wouldn't H3O plus ions increase considerably? No, because it's a buffered solution. F minus and H3O plus will increase. No, F minus actually decreases. Concentration of HF will decrease. No, nope, that's the exact opposite of what will happen. Fluoride ions will precipitate out of solution. No. 4. Of the following solutions, which has the greatest buffering capacity? So buffering capacity is how much resistance to adding acid or base can it handle? So let's think about this. If I had, let's say, my acid, and it's got a buffer if I added some base to it. The more that I have, the more it can buffer. Same thing with the conjugate base. If I add some H plus, it's going to be buffered by this. It's going to absorb there. So the more F minus I got, the more it can handle that. So we're really looking for the ones that have the most of both of those things. So this comparing them, let's see which one has the greatest of both. A is the best answer, right? It's the biggest numbers for both the base and the acid. So that's it. 5. Which of the following solutions has the greatest buffering capacity? So just like the last one, we're looking for the numbers that are going to be the biggest because they'll be able to react the most with any additional acid or base. So B will be your best choice. So now we're going to get into some math, right? All these problems essentially are going to use the Henderson-Hasselbalch equation, which, if you don't recall, it's this, all right, or some derivation of this, where B is the concentration of the base, I'll write it all out, over the concentration of the acid. There's a video I put on the drive. It's also on YouTube. If you're like, how the heck did we get this? You can find it there. But yeah, that's the equation that we're going to use. So we have the Ka of benzoic acid is 6.3 times 10 to the minus 5. What is the pH of a buffer prepared by combining 100 milliliters of 1 molar potassium benzoate and 100 milliliters of 1 molar benzoic acid? So they tell us the Ka. So let's start plugging stuff in. I know P is just negative log. So pKa is negative log of the Ka, 6.3 times 10 to the minus 5, plus the log of the concentration of the base over the concentration of the acid. Now, we got to figure out, well, what's the concentration? Because we're actually mixing these things. This one's a nice problem. It's not all that difficult because we're adding 100 milliliters and 100 milliliters. So I know the concentrations of these things are just going to be cut in half. All right, so I know the concentration of the base would be 1/2 of 1 molar, so 0.500 molar, all over, again, half of that, 0.500 molar as well. So now it's just a, beep, bop, boop. We got a pH of 4.2. That's it. Take a look at number 7. More of the same, but different. What is the pH of a solution prepared by dissolving 0.25 moles of benzoic acid and 0.3 moles of sodium benzoate in water sufficient to yield 1 liter of solution? So this was really nice because they used 1 liter, so moles becomes molar. So this is the moles of my acid, and this is my moles of my base. That sodium benzoate gives the, the conjugate base of benzoic acid. So again, pH equals pKa plus log of the base over the acid. So start plugging stuff in. Negative log of the Ka, which is 6.30 times 10 to the minus 5, plus the log of the base, which was 0.300 all over the acid of 0.250. And I plug that into my handy dandy calculator, and I get 4.28. That's it, right? All right, one more. Actually, is it one more? Oh, 2 more. 8. 25 milliliters of a solution containing 0.1 molar fluoride ions and 0.126 molar hydrogen fluoride has 4 milliliters of 0.01 molar hydrochloric acid to it. Final fluoride concentration is blank. All right, so first thing, think about what's happening. All right, we have a solution and we're adding an acid to it. So what's going to happen there? Well, it's going to react with the base that's already in solution. So what we got to do is we got to figure out, well, what's the decrease in the base? How much base was used up by adding that acid? Because it's going to change our concentrations for things. So, what's left? How much is left? And the second part is going to be, well, we got a new volume, so we get new molarities as well. So let's start dealing with some of this. So how much acid was added? Well, we got 0.0400 liters times 0.0100 molar. So that tells me that I got 0.00004 moles of the acid. Now I got to figure out, well, what was my moles of my base? All right, and that was the 0.126. Am I looking at the right problem? I'm sorry, so we're looking at the amount of base that was there. So the base is the fluoride ion. Well, we had 0.100 molar times by the volume, which was 0.025 liters, and we get 0.0025 moles of our base. So we're adding some acid. It's going to react with some of this base. So what we're really doing is we're taking the difference. So figuring out how much base is left, right? So we added some acid. We had 0.0025 moles of our base. We added some acid, so we're going to lose that much base, and we're going to get 0.00246 moles of our base afterwards. Now we're also going to change. Well, that's pretty much it, right? So now we got how many moles of our base. We got to divide that by the liters that we now have. Now we have 29 milliliters total because we had 25 milliliters and we added 4 milliliters to it. So we got to divide by 0.029 liters to give us the molarity of our base, which is 0.0848 molar. And that's what they were asking for, right? Final fluoride concentration. Well, how much did we start with? We started with this much. We added this much acid, so we know that it took away that much, which is why we subtracted it here. Now we got moles of our base, but we got a new volume here. So we got to just go, all right, divide by that volume and get the final answer, 0.0848 molar for the base, the fluoride ions. All right, numero 9. What is the pH of a solution made by dissolving 0.270 moles of formic acid and 0.230 moles of sodium formate in water to make 1 liter of solution? Ka formic acid is right there. So here again, let me circle things so I know what goes together. That's the acid, and this is our base. So again, it's the Henderson-Hasselbalch equation. So pH equals pKa, which is negative log of the Ka, 1.77 times 10 to minus 4, plus the log of the concentration of the base, which is this 0.230 over 0.270, the molarity of our acid, and that equals 3.68. All right. So yeah, Henderson-Hasselbalch equation, get used to using it. And if you're curious as to its derivation, there's a video out there for you to look it up. It's actually not all that crazy. Bring questions to class. I'll see you then.